this lesson, we are going to be talking about the statistical concept of a z-score. And in order to understand z-score, we're also going to talk about a theorem by a mathematician named Chebyshev, so Chebyshev's theorem. But to motivate this lesson, I wanted to share some information. I gathered some pulse data from my students, and the information that I gathered allowed me to know that the average or mean pulse for my students is 76.7 beats per minute. So the average student has a pulse of 76.7 beats per minute. And I also computed the sample standard deviation because this is a sample, right? The students are not the entire population in the world. So the sample standard deviation is 12.42 beats per minute. Then I took my own pulse. My pulse was at 92 beats per minute. And you'll see there Triola's pulse. Triola is the author of a really standard and well-used statistics textbook. And Triola's pulse is 48 beats per minute. And I've actually gotten to meet Triola at a math conference, and he is a very sweet guy, very chill. So that 48 beats per minute kind of makes sense. When I first told my students that my pulse was 92 beats per minute, by the way, their reaction was, lay off the coffee. Okay, so here we go. We have the data from the students, and then we know specifically my pulse is 92 beats per minute. Triola's pulse is 48 beats per minute. So here's the question. Who is weirder? Now the formal term you'll see in the textbook is who is more unusual, but I like to say weirder. It's more succinct. It's the idea across better. So who is more unusual, myself or Triola? And we are going to use Chebyshev's theorem and z-score to answer this question. So let's get started with Chebyshev's theorem. One thing that Chebyshev's theorem is going to require is that the data is normally distributed. And you probably remember from before, if data is normally distributed, then when you draw a histogram, the data looks more or less like that, swoop up and back down. So there is a visual of this data being normally distributed, and here's the idea. If data is normally distributed, then I should mention, by the way, that in the middle is the mean. So in the middle, we have the mean, mu, and 65% of the data is within one standard deviation of the mean. So if I were to go out and add one standard deviation, so the mean plus one standard deviation, mean plus sigma, and here I'm using population because Chebyshev's theorem can relate to an entire population. So we have mu plus sigma, or one standard deviation below the mean, that's mu minus sigma. We have 60, and I wrote 65, pardon me, but that should be 68. We correct that. 68% of data is within one standard deviation of the mean if your data is normally distributed. Now let's say we go out another standard deviation. Let's say we go out plus 2 standard deviations, or we subtract 2 standard deviations, mu minus 2 sigma. If we go out 2 standard deviations from the mean, and this is the truly incredible part here, if we go out 2 standard deviations from the mean, at this point we have captured 95% of the data. 95% of the data is within 2 standard deviations of the mean. By the way, if we go all the way out, 3 standard deviations from the mean, which would be, let me draw that again. There we go. If we go out 3 standard deviations from the mean, so mu plus 3 standard deviations, mu plus 3 sigma, or mu minus 3 sigma, that is going to give me more than 99% of the data. So this is how important it is that something is normally distributed and how well standard deviation works. That within 3 standard deviations of the mean, we literally have, pardon me, 99.7% of the data. So that's kind of incredible. Let's do a quick example of what the heck this means. Let's say that on a certain stretch of road, the mean speed is 65 miles per hour, and the standard deviation is 3 miles per hour. Well, the mean, mu, right in the middle, is going to be 65 miles an hour. And you know what? I'm just going to assume we know miles an hour. I'm going to leave that at just 65. Then, to go out 1 standard deviation, that's going to be the mean plus the standard deviation, 65 plus 3. This would be 65 plus 3 is 68 miles an hour. And to go the other direction, 65 minus 3, that's 62 miles per hour. So here's what we're told. 68% of people on the road travel between 62 and 68 miles an hour. All right, now let's go out 2 standard deviations, mu plus 2 sigma. So add 3 to get to 68, add another 3, plus another standard deviation, right? 65 plus 3 plus 3. That's going to be 71 miles per hour. And if I were to do 65 minus 3 is 62 minus another 3, that is 59 miles per hour. So now we know that 95% of people on this road travel between 59 and 71 miles per hour. And finally, if I add and subtract 3 again, 71 plus 3, that's mu plus 3 sigma, is going to be 74 miles per hour. And let's see, 59 minus 3, or mu minus 3 sigma, that is 56 miles per hour. So now we know that 99.7% of people travel between 56 and 74 miles per hour on this stretch of road. So that is how standard deviation and Chebyshev's theorem work. And by the way, I did this with mu and sigma, but I could have just as easily done it with x bar for the mean for the sample and standard deviation. But as you can notice, this notation gets kind of bulky. Mu plus 3 sigma, mu minus 2 sigma, that gets kind of obnoxious to write. So what we're going to do is, instead of that, something called z-score. And all z-score is the number of standard deviations away from the mean that a data point. That's what z-score is. Z-score is a representation of how far away from the mean does it fall. All right, so let's see. This plus sigma plus 1 sigma, that's 1 standard deviation above the mean, right? So this is z equals 1. And 1 standard deviation below the mean, that's z equals -1. Now, 2 standard deviations above the mean, that's z equals 2. And 2 standard deviations below the mean, that's z equals -2. 3 standard deviations above the mean, that's z equals 3. And 3 below is z equals -3. By the way, here's something that you might not have thought of, or you might have thought of. The mean itself is already at the mean. So the mean itself has a z-score of 0 because it is 0 standard deviations away from the mean. Now, how do I find the z-score for a data value? Two formulas, one for population and one for sample. So for population, the z-score is x minus mu, the distance away that the point is away from the mean, x minus mu, point minus the mean, all over sigma, because of it's the number of standard deviations away. So that is for population z-score. And then for sample z-score, it's the same thing, but just with our sample values. So instead of mu, we use x bar. And instead of sigma, we use s, sample standard deviation. So there is how you find the z-score for any x value. And by the way, what was x? X was any specific data value. So that is how I find z-score for a sample and for a population. Now, let's go ahead and take a look at something else, just so that you know. If z is between -2 and 2, right? 95% of the data falls between z equals -2 and z equals 2. And we can see that from the chart. 95% of the data was in here. That's what's going to be called usual. If z is between -2 and 2, then that is a usual z-score. However, if z is less than -2, meaning if z is out here in the unusually small area, or if z is bigger than 2 up here in the unusually large area. So, or if z is bigger than +2, then we would say the data point, or the z-score, is unusual. So anything falling in that central 95% is considered usual. Anything falling outside of it would be considered unusual, in that it's either unusually small, unusually less than the mean, or unusually large, unusually greater than the mean. So, by the way, I should mention that this is something I should say, that if z is positive, all that means is that the data value is greater than the mean. And we can see that from the chart as well. Positive z's, whoops, z equals 1, or sorry, z equals 1, z equals 2, z equals 3 are all above the mean. Negative z's are all below the mean. So if z is positive, then the data value is greater than the mean. But if z is negative, then the data value is less than the mean. So sometimes students will say that you can't have a negative z-score. That's actually false. It's totally acceptable for somebody to be shorter than average, which would be a negative z-score, or for somebody to be taller than average, which would be a positive z-score. In terms of height, short and tall, there's not really necessarily a better, but in terms of some things, right, having a positive z-score might be a really good thing, right? If I'm talking about the average exam score for the class and my z-score is positive, that means that I scored greater than the mean, so I did better than average, which is good. If, however, I'm talking about national credit card debt, then I don't want to be greater than the mean, right? I want to have less credit card debt than average. So that would be good for my z-score to be negative. So it's totally okay for z-scores to be positive or negative, and it's not even necessarily a good or bad thing for my z-score to be positive or for my z-score to be negative. Now, what we're going to do is we are going to finally finish out the original question. We are going to answer the question, who is more unusual, Adelina or Triola? And we're also, now that we know that z's in between -2 and 2 are usual, going to answer if I have a normal pulse and if Triola has a normal pulse. And I hate that term normal, right? Because normal is the normal curve, the normal distribution. So we use the term usual and unusual. All right, so let's get started. I was listed first, so let's start with me. And this is a sample. So we're going to have z equals, and remember the formula is x minus x bar all over s. And if you're doing this in a calculator, you really are going to want to put parentheses around that. So let's see. So for me, and I'll call this z sub a for z sub Adelina, this is going to be, my pulse was 92 beats per minute, so 92 minus 76.7. And I should include this information, by the way. This is BPM minus 76.7 BPM all over the sample standard deviation, S, which is 12.42 BPM. So let's see, when I do 92 92 minus 76.7, let's do that. 92 minus 76.7, that equals 15.3. So this is on the top, 15.3 BPM. And on the bottom, we have 12.42 BPM. I want to point out what happens to the beats per minute, BPM. Those actually cancel out entirely. So z-score does not have units. In previous videos, I've stressed the idea that mean, median, mode, right, we need to provide units for those. For z-score, the units have already canceled out. So let's do that, 0.42. And wow, that's a lot of numbers, right? But for a z-score, we're going to round to 2 decimal places. So this is 1.231. The 1 there tells me to leave it alone, so 1.23. So my z-score, or the z-score for Adelina, z sub a, is 1.23. Oh, wow. There we go, 1.23. And we actually know that since this is between -2 and 2, Adelina's pulse is usual. So I'm not as weird as we might have thought I was. And this is because 1.23 is between -2 and 2. All right, so my pulse is usual. How about Triola? Where does Triola's pulse fit into all of this? So I'm going to go ahead and erase the work we've just done for my pulse. And remember that those units canceled away. So the z-score being 1.23 meant that, and I should just mention this, my z-score being 1.23 meant that I was 1.23 standard deviations, since it's positive, above the mean. All right, let's take a look at Triola now. So we'll call that z sub t for Triola. And remember the z-score is x minus x bar. I'm always subtracting the mean over s. So we have his pulse is 48 minus 76.7 all over 12.42. And when we run that through the calculator, and this time I'm going to run it through the calculator all in one go. So I'm going to put parentheses 48 minus 76.7, and I'm going to close the parentheses. And notice that's already negative, and we're going to divide that by 12.42. So let's see what we get. We get negative 2.31 if I round that to 2 decimal places. So Triola's z-score, and remember there's no units, they've canceled out, is negative 2.31. Negative 2.31. So Triola is unusual since negative 2.31 is less than negative 2. So he is unusual in terms of z-score. So if somebody asks you to defend your conclusion in terms of z-score, you're going to compare that to negative 2 and 2, right? So that's what we've done. And what we do know is since his z-score is negative, Triola's pulse is 2.31 standard deviations below, because it's negative, the mean. So if you ever want to compare two data values, you can do that using z-score.